You'll go first, Jacob. 2022 question 1 and 2.
Sure, we can just dive right into it.
Yeah.
I've been yapping
Okay.
for a while about predictions for what I think will be on the midterm and stuff.
Okay.
Perhaps I could
Yeah,
be recording that, but it is what it is.
I don't think Pumping Lum was going to be on it because neither midterm had it.
Yeah.
So.
I was saying I don't think that'll be on it. I don't think like the first lecture is really important. Like just the stuff with the lever stuff. Like I wouldn't waste much time with that.
Yeah. Was that him? I think that was just him introducing the concept of like state machines,
That
right?
exactly that's what I was saying. Yeah, it's the concept of just like what can be like what kind of languages can be represented by some kind of machine, stuff like that. Yeah, that's all.
Yeah. Okay.
Okay. You can see my screen.
Yes.
Cool. Okay, so 2022 practice. We'll start with, I'm just going to go over some of the basics for this type of question. So we had something similar to this on our test. I think there's a few important things to note for this type of thing. So first off, you just kind of need to know some of the basic properties for regular expression and what it, like, what it's closed under. Like, you should know that, like, if these two are regular, then their union is regular because you can do the, what's it even called? What's the process? The subset construction, right? You can do that to create the union of the two.
Product construction.
Product construction.
I think.
Yeah. Actually, wait, or even simpler, if you're doing NFAs, right? If you have some kind of machine for the one NFA that represents A, and you've got some other machine for an NFA that represents like B, right? If this is A and this is B, then you can just make them both start states and call that an NFA, and you're done. Because you can have multiple start states in an NFA. So now you've made a machine for C as well, so C has to be regular. So this one makes enough sense. The intersection is definitely less intuitive that it's closed. I think this one is what you need product construction for. Is that correct? This is the important one you need product construction for an NFA?
Yeah, you can use product for both, but it's more easily understood for the intersection.
Yeah, because it's just not necessary for the union. As long as you're working with NFAs, you don't need it. You can just have two start states. Yeah.
But
But product construction you need for the intersection. I feel like product construction could be a question. Like it doesn't seem unreasonable to me that one of like 3 or 4 could be something about product construction. I don't know. That's just my thoughts. But it's at least useful to know because it means that you know that this, like, C is regular in this case. So just knowing these two is really important. And also, obviously, regular expressions are, like, closed under concatenation. If these two are regular, then this has to be regular. Because if you had, like, if your A was just the regular expression like that, and your B is some other regular expression like that, you just literally stick them together. Like C is just... and like in brackets, and you're done. There, boom, concatenated. So that one's not even worth thinking about. So yeah, these are all true. It's closed under all 3 of these operations. So this is like your base. You need to know this base knowledge. Everything else, there's specific examples you want to think about. So if C is regular, then D is also regular. From what I remember, this is true because this is guaranteed to be regular, right? As we know from these rules, the intersection is absolutely going to be regular. So it's a regular set concatenated with a regular set, which is still regular. So this has to hold. The second question becomes a bit more interesting. When we talk about something not being regular, I think it's helpful to have an example of something that's not regular. Unfortunately, none come to mind. So I think what you want to think about is essentially anything complicated and infinite tends to be not regular. I want to explain.
You want an example? 0 to the power of n, 1 to the power of n for all n.
I like using letters, but yeah, that works. If you got like a set like this, we'll go with that for some n greater than 0, or it could be greater than or equal to, but I don't have that symbol on me. So, and the greater this looks gross. So, this set is not regular. So if you just want to remember this as an example to think about, then sure. But essentially the idea is even if you union this with a regular set, or like concatenate it with a regular set, this part is going to be infinite and not representable by a machine. Like, there's no machine that can represent this. So if you're doing union or concatenation, your like language still has to include these type of terms somehow, and that's just not going to be possible. So not regular with like unioned or concatenated with regular tends to still not be regular. Now there's some exceptions to that. So here we have concatenation. We know this is going to be regular for sure, and we're concatenating it with something not regular. But the empty set and the universal set are really important examples to think about for counterexamples for these types of things, because the empty set is not as regular and breaks a lot of cases that would otherwise be true. So I think literally the only case where this fails is where you set this intersection to be the empty set, the null set. So when I say empty set, I don't mean a set containing the empty string. That I will specify as a set containing the empty string. The empty set or the null set just mean you have literally no strings, nothing, not even the empty string. Your language generates nothing. So that is a regular set. Because you simply have an NFA with no accepted states, means you accept nothing, not even the empty string. So if we let A intersection B somehow be the empty set, just by letting either of these be the empty set, either A or B could be the empty set, then the concatenation is also going to be the empty set, even if C is not regular. So C could be not regular all at once if you concatenate something with the null set. So let me erase this now. So if you have C, let's say, I don't have the null set symbol, so I literally have to do like this. Yeah, this is gross. Okay, hang on. I don't have a great way of doing this. I guess I can just write, like, if A equals the empty set and C equals just all this, their concatenation is still going to be empty. And I want to make sure I show why, because I know this part gets a little confusing for a lot of people. So let's say C is something else. Let's just do an example of how this works. I'll just call it B for now, actually. I'll have a B over here. So when you do concatenation, let's do this example. If you do concatenation between these two sets, then you are basically taking every combination of all the values here and concatenating them. So this concatenation becomes, you do 1A, you could have 1B, then you could do 2 with each of these, so you concatenate 2 on the front, you could have 2A, you could have 2B, and so forth. Now, let's say that we have A is still, or we'll do C. We'll have our C is just the empty set. This is nothing. So it's kind of hard to show an empty set containing the empty string, but I'll usually denote it like that, where it's like an empty pair of quotation marks. In which case I should technically be doing like this for everything, but that takes a lot of time. Well, I'll do it anyways. Screw it. This works. Alright. So C is literally, this contains nothing. This is null set. This is like the 0 with the line through it. That maybe I should just get that symbol. Null set. Go. Awesome. Okay. Oh, that looks gross in Notepad. Okay. And we'll have the B is still the same set from before. So if you're trying to do the concatenation here between these two, and you're like, oh, okay, yeah, I'm going to go combine A with every element in C. Well, there's no elements in C. Okay, let me go combine B with every element in C. Well, there's nothing. So you still have the empty set. You still have the null set. Meanwhile, if we had a similar example where instead it was the D is just a set containing a single element, the empty string, well then now when we concatenate B and D, you get A concatenated with every element, so you join A and the empty string and just get A. Then you join B with the empty string and just get B. So this is why concatenating with basically epsilon is like, it's like the identity element. You just get the original set if this contains epsilon. But if this is the null set, you get nothing, because there's nothing to concatenate with. So that distinction is really, really important to understand for this type of question. And just for a lot of other types too. I feel like this comes up fairly often, actually, in TB3 too. Okay, all that yapping out of the way, essentially if we make this the null set, by making either A or B the null set, then C can be non-regular, but D would still be regular, because the end result of this concatenation would still be the null set, it'd be empty, which is still a regular set. Okay. I just want to check any questions about that. Yeah, the null set is regular. Wait, we're saying the empty set C is not regular? That's not what I was told. Because I think assuming the NFA explanation makes sense, right? Like you can have an NFA that has no accepted states. You don't have to have accepted states.
Yeah, the null set is regular.
Yeah. So empty set is this. Empty set or null set I consider to be the same thing. I think that terminology is correct. That this is the empty set and the null set. They're the same. And then this is the set containing just epsilon. I don't have like a way of writing epsilon really, but this is a set containing just epsilon or just the empty string. Those two are different things. Do we have it? Yeah, for null, it's just if you have no accepted states. If there's no accepted states, then your DFA accepts no strings. I see people typing, so I'm just gonna let questions happen, and then I'll go on to the next part.
I think the confusion is like coming from the fact that we have to remember that the set we're trying to like define is the languages that are accepted by a DFA. So if the set is empty, it means your DFA can be as many states as you want, but as long as there is no final state, it means nothing gets accepted, so it's still null. So if you're trying to imagine an empty DFA, that's not really the case. It's an empty language, not an empty DFA.
Yeah, you can have a ton of sets, but you can have a ton of states, but there's no accepted states, so there's no possible string that your machine would accept. So AC works. Let me get AC back open again. I'm gonna toss this. I can actually make this a bit skinnier. There we go. Oh wait, I didn't actually write what AC was. Okay, hang on. So AC works if C is. Oh no, hang on. We're looking at actually this question. I think. I don't even know. Okay, hang on. AC works if C is an L set, but not A intersection C. What do we mean by this? If C is an L set. No, I'm actually not sure what you mean by this question. Gabe, do you know what he's saying or?
No, I'm not really sure.
Okay. I'm gonna start on this next part, and I'll come back and see if there's any other questions to answer. Okay. So next up we have if C is regular, then this always holds. Distributivity of concatenation over intersection is not true. Does not exist. I'm going to delete this now. Click. Okay. So this is just an important counterexample to know. I feel like I only know this because I Googled it once and it's come up a lot. Because it was on a quiz early when we had this course, and then it was on this, and then I think it was literally also on our actual midterm. So I'm just gonna go through the counterexample. This is just something you should know, that there's a lot of cases where you can create two sets where they have no intersection, but when you concatenate them with another set, suddenly there's an intersection between them. I am recording, yes. Yeah, I got OBS. Woo. So, yeah. Okay, so there will be some cases. There's a lot of cases like this. I think you can let this be like empty, and you can let this be something. But you'll see that if we have these two sets, and then we concatenate them with C. These are going to be my options. So when I concatenate A with A with this part, right? That's where I'm gonna get 3 A's in a row. And when I concatenate B with this part of C, I'll get 3 A's in a row. But the important part is that there is no intersection between these two. But then when I concatenate them, suddenly we have an intersection. So when we look at this, and this part can trip people up because they think about, let me start this. So when we do, okay, I need to do AC. Sorry, no. What I want to do is I want to show that if we do this, so A intersection B is going to be equal to the empty set, right? It's going to be equal. We got nothing. We got nothing here. And then once we do all of that concatenated with C, we still get nothing, right? Because this is the null set. Concatenation with the null set gives you nothing because it's supposed to take every element in C, put it in front or put it behind every element in A intersect B, but there's nothing here. There's no elements, so you get nothing, right? This is different from if this had been the empty set containing epsilon or containing the empty string. So we can see that case. And then the other one we're trying to compare it to is if this if it's the same as this, right? We're trying to see, are these two D definitions equal? So actually, I'll keep that down here, but for now, we care about AC. We can see that AC, the intersection between, or sorry, the concatenation of these two, right? We get AA, and we get that AAA I was pointing out earlier. Let me scroll that down a bit. And if we do BC, right, again, we get that AAA, that's the important intersection, and then we get the quadruple A. So when you intersect these, there is actually an intersection. So again, there's a lot of different ways to create an example for this, but it's just important to know that you can have two sets with no intersection, but when you concatenate them with the perfect set, then you can suddenly have an intersection, and that's what breaks this case. Okay. Just gonna quickly look for questions. Nothing. Okay. Next one was, if C is regular, then this never holds. Okay, so for a lot of cases like this, one of the most trivial examples to look for is just setting everything to null set. The null set is always like amazing for these types of examples. If we just set all three to the null set, it's quite clear that these are equivalent. So, done. So this does hold in this case. And then we'll look at the last one here. If C is not regular, then we're saying that this equality never holds if it's not regular. So this would circle back to what I was talking about earlier, that often when you're trying to concatenate with a non-regular set, you have to include that non-regular set in your machine somehow, and that's just not possible. But in this case, it is, because we can totally set, I think, if I remember this correctly, I think the idea is that, I'm trying to remember it. If this can be null, like if A and B is null, then when you concatenate it with C, you're still getting a regular set. Or no, sorry, you're getting the null set. And then here, if A is null and B are both null, then you're still getting the empty set. Yeah. So as long as you set A and B both to the empty set, to the null set, then you get the same thing. You still get the null set. Even no matter what C is. So a lot of cases where it's talking about like, oh, C is not regular, but does this thing have to be not regular? You're just basically looking if can you eradicate C with the empty set is what you're looking for in a lot of these cases. Is there some way you can concatenate it with the empty set, or intersect it, or union it with the empty set so it just is gone? Sorry, also, if you intersect a non-regular set with a regular set, it has to be regular. I think that's true, at least. Because you can think of it as the regular set is restricting the potentially infinite non-regular set to be, whatchamacallit?
Yeah, there will always be a non-regular component to it.
Yeah, exactly.
But only if you add a null set. If you concatenate with a null set, then you're eradicating those non-regular components. That's like the only case, yeah.
Yeah. Okay, so any questions about this first part then? Union always holds. Union with what? Like union, like regular, union, regular is, or what are we saying here? Or union regular, like non-regular is always non-regular. What do you mean?
Yeah, I think that's what he meant, and no, it's not. And there's an example in like the 2024 midterm. When we get to it, we can go over that, where you're supposed to come up with a set unioned, a regular set unioned with a non-regular set that's still regular, and there is an example.
Oh, actually, I don't remember that. Wait, I'm trying to think. I want to see if I can figure what that was on the spot. I mean, okay, well, we'll come back to it. We'll get to that. Yeah. Okay. These questions are always fun. I like thinking about these. Okay, I don't feel like there's actually too much to say about this because 3 of them are obvious, and then there's whatever the heck this is. But I'll go into it anyways. I at least want to talk about the difference between DFAs and NFAs and make sure we all understand them. So DFAs are great because they are deterministic. Them being deterministic gets really, really important when you get to 3TB3, where they're actually being used for programs and stuff, and you need like a program to actually go through them in some kind of procedural way and find out what languages are possible to represent. NFAs suck. If you try to run a program through an NFA, it's terrible, because an NFA can at any state, right? If at any state here, let me clear all this. Goodbye. Okay, at any state here, you can go to these two like with the exact same label, right? So if you're trying to read some string that's like, you know, A, B, like you don't know where, when you start here, you don't know where you're going. So NFAs suck for compilers to read. Also, you don't even know where you're starting half the time. And sometimes you just get to something, actually, no, the fact that there's no, the fact that you're not required to have a B going to like a garbage state though isn't actually important. That one's fine. Okay, but yeah, so as for the actual differences, so DFAs, you can't have this is not allowed, right? You can't have you can't have the same label go into two different states. And then for your entire alphabet, like let's say all my transitions are A and B, at each state you have to have A and B. And if one of your states suddenly has a C transition, or hang on, if one of these states suddenly has a C transition, this has been added to your alphabet, every single other state also needs to have a C transition going somewhere. And that's why often you'll have like a garbage state that's just meant to be like, oh, okay, C, if it has a C at this step, it's definitely not in my language. It goes to garbage state, you know? If after doing a B, you've got like a, definitely not in my language. You got your garbage state. NFAs don't need this. The NFAs, this is just implied. If you don't have a C, it's just implied that there's like a garbage state there. And then yeah, so in NFAs you're allowed to have two the same transition go into different states. In DFAs you can't. And in NFAs you can have multiple start states. Also, I think he kind of talks about it later that NFAs are sometimes allowed epsilon transitions, but that one's kind of shaky because epsilon transitions are even worse. Because then, like, let's say you're here at each step. If there's an epsilon transition, again, you don't know if you're taking that epsilon transition or if you should be going this path. They make all that even worse, and they break a lot of definitions. So epsilon transitions suck, but technically you can make stuff with them, and it kind of makes sense. Back to all this. The language corresponding to some NFAs cannot be represented by DFAs. Wrong. These are both. You can always convert between these two. Right? I'm not making things up there. You can convert between the two. I feel like I'm just gonna like spread a lie at some point in this because I feel like I forget half the material. But from what I remember, these are completely one-to-one. You can always convert one to the other. It sucks because converting any kind of decently complicated NFA to a DFA like can sometimes like you get like just more than double the states. It's awful. Some regular sets are easier to be represented by NFAs than DFAs, since any equivalent DFA will have exponentially more states. And yeah, that's completely true. Just NFAs tend to be they exist because they're easier to ration about. Like the whole like think about how we talked earlier about when you want to union two sets, that this is easy because you can visualize this easily that this is regular still because you can just have two start states on the NFA. Like the NFA can just have two start states, one to start on this machine and one to start on this. NFAs just make it way easier to rationalize about what's possible to represent and what's not. And it's important that they can be converted one-to-one with DFAs. That whole property is why they're useful. But DFAs are kind of like our goal. DFAs are great for compilers and they're our goal that we're working towards, but NFAs are less complicated and represent the same thing. Would they ask us to draw out NFAs, DFAs for the midterm? Yeah, they totally could. In 2022 on the question 3, they absolutely do. You don't understand how the 5th choice is different from the 4th by making C not regular from question 1. I'm gonna assume Gabe's answer clarified. If it didn't,
he's asking because the question 4 says if C is regular, and then if says if not regular, and he's asking what's the difference.
Oh, okay. I guess I see what you're saying. Well, I think the idea is that you might think that this one's true and this one's not true. But yeah, in either case, if you just set A and B to like the null set, then it really doesn't matter what C is. They're just always equal.
Yeah. That's a good answer. Mm-hmm. It's basically like you'd think that in a multiple choice or whatever, one would be true and one wouldn't. Like someone would assume that. But in this case, neither are true. They're both false.
Yeah,
so
the fact they're both false is kind of showing it really doesn't matter what C is. Yeah. Mm-hmm. Okay. Yeah, and then I literally don't know. I had to ask like TAs, and they also had no clue what we were talking about with patterns. I literally don't know what this is talking about. This patterns thing. We didn't have anything talking about patterns on our midterm. I don't know what they are, so I can't tell you anything about this one.
I think it has to do. This is a long shot, but I think it has to do with that. I remember tagging you once, asking you what the at symbol was, and it was only really defined in the textbook. You couldn't really find anything about it online. So I think it has something to do with the textbook, but I'm not sure.
I wonder, maybe it's like content they covered back like in 2022. I don't know. This is just strange to me. I don't even know what the answer to this question is. Like, I don't know what the answer is supposed to be. If anyone has insight on patterns, it's defined in the textbook. Yeah, okay. For the Q1, only the first one is correct. Is that what I said? I think so. Yeah, I think everything else is a counterexample. Yeah. Okay, and then lastly, any regular set can be represented using DFA, NFA, or regular expression. Yep, that's just an important definition to know, right? If that's kind of the whole way we rationalize about regular sets is they have to be represented by one of these three, or all of these three. It's the same thing, and all of these you can convert between any of these three, right? If you can make a DFA for something, you can make a regular expression for it, or you can make an NFA for it, and that applies always between all three. Got more characters. Okay, so I think the idea is like the patterns are okay, yeah, this seems right. So all regular expressions are patterns, but not all patterns are regular expressions. Which means this is probably false. Yeah, this has to be false, right? If we're saying any regular expression is a pattern, then if you can represent something with a regular expression, you can represent it with the same pattern. So this seems false, if I'm understanding the idea correctly. I think patterns are kind of just like regular expressions, but you get some more symbols. What's the difference between regular sets and regular expressions? Great question. A regular set is the actual set of strings. So this here is a regular set. The regular expression for this would be that. So this, like this string here, like this here is the or like I should maybe just write it like that actually. This is a regular expression that defines this set. So we could say if A is a regular expression, we set to that, then the language of A is equal to this set. So the language of a regular expression is the regular set that it describes.
It's kind of tricky to think about, but language is like, I like to think about dictionary. When you open a dictionary, there's like 100,000 words. So it's like it's a set. It lists every string, every word, every possible combination of the symbols in the language that make up the strings. A regular expression is just like an expression that you pattern match on, like the A plus AA, or it's probably easier if you make like A star. A star and the language representing A star, while the set is infinite, but the regular expression is just A star. If you want to show that, Jacob, like A star
okay.
and what would,
Yeah, so we just had A star, then its set is literally going to be all of this, like dot dot dot. So it's way easier to actually represent it like this. You can't, writing out this is terrible. I don't know what else you wanted to, is this all you wanted to show off as an example, or?
Yeah, that's it. So the regular expression is the thing that you can build the language from using a pattern.
Yeah, so it's a simplified expression to represent a more complicated set.
Yes.
Can I explain why the third one's wrong? For 1 or 2, you want me to go back over 1 part 3? Yeah, the regular expression is just another way of defining a set. Because in theory, like we have our set theory, right? We can represent this as well. This set could also be represented as a to the n for some n, you know? But regular expressions often are a more simplified way of representing them. And there's just some important properties about sets that can be defined with regular expressions that are just very useful to have. This course seems weird because it's just working with like a lot of arbitrary definitions, but it makes like a lot more sense once you get to 3TB3, where you kind of start to realize why these things are important, I guess. Yeah, the language of the regular expression, the third choice from question 2. Oh, okay, yeah. So again, I don't know how important patterns are to actually know, But a pattern seems to be, it's like, oh, you have a regular expression, but you have more symbols and stuff. And I don't remember what these do. But the important thing in that case is if it's just a regular expression, but you have more symbols, then if you have some regular expression like this that represents your language, then why, if you're trying to represent it as a pattern, why wouldn't you just use the exact same expression, right? If you have all the same symbols available plus more, there's no reason when you're trying to represent this regular expression as a pattern that you wouldn't use the same expression. So there's no reason that any equivalent pattern would have to be longer. They should actually all be the same length or potentially shorter. There's no reason a pattern would have to be longer than a regular expression that represents the same set. If I'm even understanding patterns correctly, because I literally just went off whatever Pablo set up here, which is just this.
Yeah, I think the pattern is like we have more things at our disposal.
Mm-hmm.
But a regex is still a pattern.
Yeah, there's also stuff called extended regular expressions that you guys haven't learned, which is like you got square brackets that mean like, oh, this A is optional and stuff, so you could represent this language like this. This is that same language I was doing before, where it's A or A. This gets exciting. Ooh. You don't need to worry about that for now, though. Yeah, okay, they've got all this garbage. Yeah, okay, lovely.
It's funny how you can't find any of that online, but on the textbook, like ChatGPT has no idea what that is.
Oh, yeah, it's so made up. It's so made up. It's crazy. Yeah. Also, regular expressions literally don't do plus for or is so fake. I don't know where that came from. Regular expressions, proper ones are it's a pipe. You do this. This little pipe is or. That's what you do.
Yeah. I don't know where that.
I don't know where the plus comes from. It's baffling.
Yep.
Yeah. And the plus actually has a meaning. In regular expressions, it would be worse if the plus was like just an unused symbol, but plus literally means like, this means one or more times. Like the star means any number of times, but the plus in actual regex means one or more times. It's terrible that they're just changing the syntax of regular expressions. It's horrendous.
Yeah, remember when I asked this at the beginning of the semester? I was so confused.
Yep.
Yeah.
Anyways, not trying to confuse you with all that, because the important things to know are that you have plus for or, star, and brackets, and that's it. That's all you got. Okay. If there's no more questions about this, then I think we're good to go on to 3. Which questions are correct? You're right, I kind of forget to write actual answers for this. For 2, we got A. Wait, we got A was true. Wait, no, false, very false. What am I saying? I misread the question. Alright, for B, also false. Yeah. And then C, oh wait, are they all false? No, the last one's true. Is that right?
Yep.
I think that's right. Yeah, okay, cool.
Jacob, before we move on, you want to try tackling the question of what even is something being regular? Because I feel like that confuses a lot of people, like when we say a set is regular. So if you want to try answering that.
Okay. A set being regular, the best way to think about it in this course is that you can represent it as a DFA or an NFA or an expression, but I feel like the machines are sometimes the easier ones to think about. I'm not sure where exactly you wanted to go with this, Gabe. We can go into what's not regular.
Okay. Well, the idea I had in mind is just that something being regular can be represented using a DFA, but a DFA is something with a finite amount of states. So if you need an infinite amount of states, then that's where you go into non-regular territory.
Right. Yeah, we were talking earlier on the Discord about a lot of people had questions about like how should you know if something's regular or not regular. So the big one, Gabe made a great point about memory. You want to think, there's 2 ways to think about it. One of them, I use both ways. By the way, Gabe, like when I came in talking about like, think about infinite states, like I also use what you thought about with the memory. So let's say we have a set like AN, BN. There's a few ways to think about this. And if they both line up, then you know you've done something right. So if you have a set like this, as you start, this set would look like, it would look like this. You'd have AB, AA, BB, AAA, BBB. So for every number of A's, you have to have the same number of B's following it, right? In a set like this, it's impossible to represent this with a regular expression. This cannot be a regular set because of memory. When you start to add A's, you need to remember how many A's you added so that you can add the same number of b's later. And any time that you need some form of memory in a regular expression, you're stuck. Because the other way to think about this is if you want to do an NFA for this, if you want to do a machine, then what you would need, I'm losing my train of thought here. Yeah, okay, so let's think about this. One example I liked that you guys had we had in one of our assignments. I don't know if we even have the same assignments, but it was something about making a machine that accepts any string of A's as long as it's divisible by 3. Like the length is, so it would accept like anything like this. As long as the length of the string was divisible by 3, then it would accept it. And the way you make a machine for this is you have a start state. We'll actually number these states. We're going to number these states by the remainder of how many A's are left over. Actually, wait. First, I should even check. Did you guys have this question or no?
We had that question, yeah.
Okay.
First
I do want to just go over it because it's honestly, this is an example I think about all the time. Like this specific assignment question, I come back to this all the time in my head, so I'm writing this out anyways. But you guys probably had something similar where you essentially wanted to write the remainder after if you were to divide the number by 3. So if you start with nothing here, so if you want things divisible by 3, then we want where, I guess I should have included, technically you'd have the empty string would also be acceptable. But the idea here is after 1a, right, if you're now in a state where the remainder after dividing by 3 is 1. And if you take another a, you're now in a state where the remainder after dividing is 2. And if you take a third one, then now your remainder is 3. And if you keep going to the cycle, if you have 4 a's, you'll end up here where your remainder is 1, and so forth. So this one's easy to represent because you can make a state for every, you can have a single state for basically every state you can be in while you're looking at a string. And then let's look at an example where you can't, which is literally this one. For this, as soon as you take a single a, you are now in a state, let me actually draw this one out. You're now in a state where you need to take that many b's to get back. So if we start, actually this should be the accepted state. So if I draw out here, I'll call this, the P is going to represent that you have that many A's. So if you take 1A, then you're at a state where you need to take 1B back. That's easy to represent. If you take another B, or another A, right, now you're at a new state where you need to take that many more B's back. Like you need to take 2 B's back now. From P2 you have to take 2 B's back. And you can't simply connect back like this because then you can take more A's forward. So this means you require a whole other state to get back, which we'll call Q1, to show that you need that many B's to get back. And again, if you take another A, you're in another one where you need 3 to get back. And as you can see, this is just going to be infinite, right? You need another arrow to get all the way back here. Or is this even? Yeah, you would need like a whole other state. And you can see this is just going to require infinite states as this goes on, right? At each number of A's you can have, you're at a new state where you need that many more B's to get back. So there's no way to represent this as a machine. So those 2 A's just kind of the brief way of thinking, does this use memory? And then the slightly more complicated way of thinking about it of how would I represent the state that I'm in at any part in the string. Those are kind of the 2 ways of thinking about is an expression, or is like a set regular, or is it not? I don't know, anything else you wanted to go over on that topic, Gabe? Or?
No, it's okay, we can move on.
Okay. Okay, then I'm done with these 2. If you can share if you want to go over 3 then.
Yeah, I think you need to stop sharing for me to get that
that's
option.
how this works. Sorry, let me stop that.
Yeah.
Okay.
Okay. Can everyone see my screen?
Wait, I'm trying to figure out how to full screen it so that I can, because I'm recording. It's not letting me really full screen properly. This is not great. I don't want to keep this like really tiny. How do I? Alright, I have a new plan. I have a genius plan. I'm simply going to go into the recording and just zoom in the recording. Oh my god, this is gonna look so awful. I'm like editing my layout live. It's beautiful. Alright. That's I think I have like killed the aspect ratio. Like I've stretched it a little bit. It's fine. Actually, wait, I'm resetting. Fit the screen, and then I think you have to hold Alt. Yeah, and then it preserves the ratio. Oh yeah. Nope, that's cropping. Is it hold Control? Nope. You hold Shift, of course. Alright, there we go.
All good?
Almost. You're probably good to start. Wait, no, hang on. No. Oh my god, I made it worse. Wait. Okay. That is probably as good as it's going to get, I think. It's close. Yeah, it's fine. It's fine. It should be okay.
Okay. So question 3 is asking us to draw an NFA for some regular expression. So the regular expression given is this, and as you can see, like the first thing that I notice when I look at this is that there is an OR separating two different regular expressions. And the thing with NFAs is that you can like technically choose where you want to go. So for the two things separated by that OR, you can make two different transitions from the start state. If you're part of this regular expression, you'll go that way. If you're part of this one, you'll go this way. And it's pretty straightforward from there. I'm just gonna I'm gonna do the first one here, and I'm gonna read from right to left. So from left to right, sorry. Here we want to accept an A followed by another A, and then we want to accept the A or B clean start. That means we want to accept as many repetitions of A and B as possible, whether it be 0 times, an infinite amount of times. The best way to do that is just to do a self loop, where because the A plus B starred can be nothing. It can be A, B, A, B, whatever you get, it's still part of the string. Like you're not disqualifying yourself. But the easiest way to represent it is just self loop. Usually with a star, you'll have it represents a loop. And then you finish off by taking another B and another B, and that marks it as a final state. And you do the same thing for the other one. This one, you go with a B, another B, A, B starred, so you can self loop on the spot, and then A, mark it as final, and that's it. I don't know. This is a pretty straightforward question. Does anyone have any questions? You would get marks per each. Okay.
They're like yapping about the multiple choice grading scheme.
Yeah, okay. Yeah, I'll assume that everyone understand this pretty well. We can move on.
Only things I would say for this are like a star is like always a loop. Like I don't think there's any other way to do stars.
Okay.
But sometimes it needs to be like a multi-step. Like maybe you need to go between 3 states in the loop. Depends on how complicated the expression is inside of the star. And a plus is pretty much always going to be a fork in your path. You go either way. Like this is like what you did at the beginning. As soon as you see a plus, you just split. You got 2 options.
I see. Okay. Yep.
Yeah, they could both go to the same state as the final state. That would be fine. As long as there's no arrow going back out of the state. Basically, these machines only get complicated when there's like an arrow coming back out of a state, and like that can mess with things if 2 things meet up, and you can start going back through the other one's path. Like, yeah. So you can draw real quick that they both go to the same one. The only case where this sort of thing gets weird is if there was an arrow leaving this state to go back somewhere. Like if this machine could loop because it had been starred or something. Like then you get into some awful cases. But as a midterm, like, I'm hoping any midterm question you guys get would be nice and simple like this one. If it's A, B star, okay, let's, Gabe, as an exercise, let's do this, but assume it's A, B star and not A plus B star.
Okay.
Okay, you didn't have to erase the whole
Oh, yeah, okay.
thing. Yeah, maybe
Okay,
just cut
so
out, like,
I
the
think
left
what
half of it, or the right half, I mean.
Yeah, so A, B star here.
Yeah.
So again, I'll do the first half. A again. Then we want to do A, B star. I think it would have to be A, B, and then A.
No, I think it's the B should bring it back. I think it'd be like A to the one state and then B back to the same one.
Oh, yeah.
Yeah.
You're right.
So make sure for stars that you're ending up in the same place you started at the beginning of the segment that's supposed to represent the star. So this whole, like, because that third A is where we started our star, like, we need to make sure we're coming back to there, and make sure that to move on to the next part of the string, that you could make sure you can skip the loop. Like, make sure the loop isn't forced. We need to make sure for the next part of this diagram now that we're not continuing after the third A, we're continuing after the second one on that state. So not from there, we're not continuing from there. Because that forces us to do the third A. Yeah,
well, it's an NFA. It's an NFA, no?
What do you mean?
We could just go on B like this, no?
Doesn't that force and a third A when it shouldn't be required?
A, B.
That
right.
forces you to, you have to take A, yeah. So you have to make sure you're going from where your star loop started is where you should continue the rest of the expression from.
Yeah, because if you do it this way, then you'd have to do A this way, B that way. So that's our first AB. And then we want this BB here. But to get to the BB, we'd have to go through A again. So we just messed up our NFA.
Yeah. Pavlos, no. So epsilon transitions are never required to represent anything with NFAs. Like, anything you can represent with epsilon transitions can be represented without. Oftentimes, it's just more complicated. Epsilon transitions are only meant to function as a one-way. They're essentially like a one-way transition, because sometimes you run into issues where you're allowed to go back into the machine itself in cases you aren't meant to be able to do that, and like it breaks things, and it makes the machine way more complicated than it needs to be. If you're just trying to show the empty string, you just need to make the initial state accepted. If your initial state is accepted, then you can accept the empty string. That's all you need. Does that answer your question? Cool.
Could you show how epsilon transitions work in this case?
I don't know how you'd even use one. You wouldn't need one here.
I think the only epsilon usually, like epsilon transitions in NFA, just allows you to stay in the state you're in, no? I think we'll see that over here, actually.
I don't think we'll see epsilon transitions in this one, no.
No, for question 4.
No, that's what I mean, yeah. If you're just trying to do the recursive definition, why would you see epsilon transitions? Because you're not making a new machine, if I remember how this works at least.
Well, I'll start, I guess, and I'll show
it. Okay, yeah, go ahead.
Okay, so yeah, we want to do the regular expression using the recursive definition. So the way regular expressions can be represented with that formula he showed in class, it's that alpha here, which is the regular expression. Or if we want a regular expression for the entire NFA, then remember, an NFA accepts the state if you go from the start state to the final state to some final state, passing through any state in the NFA. So this definition right here is like it's you represent it that way with the UV at the bottom and the R at the top, specifically to represent the start state, the finish state, which in this case are both Q0 and Q0, and you pass through all states in the NFA, which are Q0 Q1, Q2. That was kind of a bad explanation, but does anyone have any questions about how you're supposed to read this syntax over here? There aren't many resources about it online, so yeah. Let's see if any. Jacob, is anyone asking about what this?
No, no one's. Someone's typing at the moment. Yeah, someone said it makes sense.
Okay. Okay, so one way to, so the general formula is kind of long, but it's pretty easy to remember once you like actually understand what it does. And essentially, it allows you to split up your NFA into two parts by removing a state. So if you remember, recursion is kind of like reducing and simplifying your problem until you get to a base case. So this is the same thing. This is why we call it the recursive formula. You essentially make your question simpler and simpler until you get to a base case, which you can solve very easily. So what we mean by that is, let's pick a state to remove. And here there's actually there is a state that you can pick that would make this problem easier to answer and less work. And that would be the state Q0. So I'll show you what the general definition looks like if you don't pick Q0. So over here, we will remove, let's say, Q2, for example. So this is, I'm following the general formula. It's Q0, Q1. So how do we go from Q0, the start state, to Q0, the final state, passing only states Q0 and Q1? Or, so there's two ways of traversing this NFA. Either you don't go through Q2, the state we removed, or we go through Q2, which is start state to Q2. So we're going through Q2. Looping as many times in Q2 as we can. So Q2, Q2. And then from Q2 to our final state. So this is how I remember this formula. Yeah, so someone just sent the general formula here. You pick a state to remove and you go through it. So over here we picked Q0. So now going from the start state to the final state without passing through Q2, or we pass through Q2 like this, by going to Q2, looping as many times in Q2 as possible, and then going from Q2 to our final state. So we split up our problem, and this makes it easier to answer. But if you see here, now there are 4 different terms that you have to calculate. There's this one, that one, that one, and that one. And that kind of, you'll have to do recursion on each of the terms, and that might take you a while. So if you've done assignment 2, you can notice that actually the easier way to do this is by removing Q0. Because that just gives us Q0, Q0, Q1, Q2 as states we pass. Or we go through Q0, but that's just Q0 to Q0 again. So as you can see, we're just repeating the same term over and over. So you actually only have to do the recursive definition once, and you'll be able to replace all the terms with it. Q1, Q2. And that just leaves us with getting one of these, and then you could plug it all in. So we'll do that right now. I'm going to move to a different page. So now we just have to find Q0, Q0, passing through states Q1, Q2, and applying the general formula again, we can pick a state Q1 or Q2 to remove. I'll pick Q2. So we either go from our start to finish through Q1 only, or we force passing through Q2 by going from Q0 to Q2, looping at Q2, and going from Q2 to the final state. And now we've reached our base case, because this is pretty easy to answer. So for the first term, how can we go from Q0 to Q0 passing through state Q1 only? Well, this is what I was talking about, Jacob, where you have two options. You can just stay at Q0 with the epsilon, or you can go to Q1 using an A, and you can come back to Q0 with an A, so AA.
Okay, so this I don't remember, but I remember thinking about it. What does it mean to be like basically going from Q0 and Q back to Q0 and all that, but like where Q0 isn't in your set of states?
Over here, right here?
Yes. What is it
So,
like? What's the difference between having this and then having this where Q0 is also listed in the states?
Okay, so very good question, and that actually I got stuck on that during the assignment for like a couple hours, and ChatGPT wasn't even able to answer it. But the key here is I was gonna ask if anyone knew why the answer is epsilon plus AA and not epsilon plus AA starred. The answer is AA, but you would think that if you can use Q1 as a state, then you could technically go A, and then do it again and again as many times as you want. But if we look at the first case where we go from Q0 to Q1 on an A and back to Q0 on an A, this is our start state, this is our final state, and everything in between is intermediate states. And the intermediate states are the ones that go in the set over here. So if you were to go back to Q1 and do that thing over again, then Q0 falls into your intermediate state, which you can't do. So you can only start and finish at Q0. If you leave from Q0 anywhere in between, then Q0 is technically considered an intermediate state, which it cannot be because our intermediate states are given in the exponent over here. So that's why the answer is AA, not A starred.
That's correct, Yay Turtle. Yeah. Yeah, as long as Q0 is in the intermediate states, then you can keep doing the loop. So it's not that you can only visit U or V once. That's not like as long as U and V are both in your set of states, you can visit them as many times as you want.
That is correct. Oh, I'll leave that.
Yeah, I remember thinking about that, and I could not remember what the answer I'd come to was.
Yeah.
Because I think that's the main trick with dealing with these questions.
Some people are typing, so I'll let them ask before I move on.
Mm-hmm. I'm like high-key paranoid. I've like messed up the recording and cropped it wrong, but it looks pretty good to me. I think. The problem is when I pop it up, I'm like recording my screen. So if you've ever done like screen recording, you know, if you're like recording your whole screen, you open up your capture device, you just get the infinite mirror.
Yeah.
I've got that going, and it covers the part of the screen I want to see.
Oh yeah.
Wait, I can move it. Oh my god, I forgot I can move it. Okay, yeah, I think it zoomed in fine. I can just move the OBS tab. Am I dumb? I think so. All right, it's fine. It's fine. And they can only see this epic corner of the chat. It's all good though. I think we've been pretty
Okay.
good at reading out chat questions, so it should be fine.
So only when you and V are not in the States, then the rule applies that we can only visit them once. Well, yes, I guess, in a sense. I like to think visit are for the states that we visit along the way. If you look at like the formal definition of the prof made in the lecture, it says that the regular expression, like given by alpha, is the states that take us from it's the set of strings that can be obtained going from U to V, visiting only the states in R along the way. So R along the way.
Everyone's getting to watch me like mess with my OBS in the recording because I just misclicked and I totally like fucked up my crop, everything. Oh no, I fixed it. We're good. Okay, it's all good now. I was zooming out so people could see the chat and it became a disaster.
So if Q0, okay, yeah. So if Q0 was in our states, we would do epsilon plus AA star. That's correct. Sorry if I missed it, but you said the question is easier by removing Q0. How do you recognize which state would be best to remove to solve the question better?
So your goal is to remove infinite loops is definitely the big thing. Would you agree, Gabe?
Infinite loops.
Well, like your goal is to eventually get it to cases where you can't have, because in this case, if we look at this, the only reason this is difficult as a regular expression is because there's 5 bajillion infinite loops you can take, right?
Yes.
So our goal is removing those. Is kind of the.
I think his question or their question was, why are we removing Q0? How did we like? So this is the one that you ideally do not want to do during the midterm because you'll have to recursively do the definition for all the terms inside since they're all different. But remember, Q0 is both our final state and our start state, right? So if you remove Q0, remember the general formula says when we remove a state, we either go from the start state to the final state going through all the states minus that state we removed, or we go through that state. But if our start state is both, our start and final states are both Q0 and Q0, then removing Q0 means that over here we just keep the same thing in like that expression. Whereas if you remove Q2, you'll end up coming up with different terms because over here you remove Q2, so you go from start to finish without passing through Q2, or you pass through Q2. But if your start and final state is the same, then passing through it doesn't change anything. So that's why over here, it's Q0, 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 and they're all the same term. So you only have to do it once. Is it important to show this entire working? If you look at the solutions, I believe, yes, they showed all of that.
Yeah, so we were marked for each individual step we wrote. I think, okay, sorry, our midterm was weird. Our midterm was different, actually. It was different from this. If you do get a question like this, you probably should be writing out your formulas for everything. But this question only specifies, like, write a regular expression for the whole thing. Was that right? Or what was the end goal?
Correct, but I don't even see how you would do it without writing it.
Yeah, I mean, you should be writing this. Yeah, I don't know what you would do. The one thing I asked him about is I asked if it was okay to only write, like, 0, 0 instead of, like, Q0, Q0, because it just wastes time. And they said that was fine. So it'll save a lot of time if you don't write out the letters, for sure.
Also, should we remove the start state in general for these questions? If your start state and final state are the same, then yes. I would remove the start state because when you do this section of the formula, your denominator wouldn't change. By denominator, I mean that part right here.
So just quickly back to our midterm. Ours was different. It was you were just told like, oh, write out like this part of the formula. Like it would just tell you, oh, write out the definition or like write out the regular expression for like using the states Q0, Q1, Q2 from like starting at Q0, ending at Q0. Like, it would just give you one of those to do. And I think it gave us like 4 of those. Yeah.
I think in your midterm, you literally just got this one.
I think it was this, but like broken down, where they basically told you which steps to do. Like, you didn't have to guess how to break it up. They just told you a process to do.
Exactly. It broke it down for you. Exactly.
Yeah.
By the way, I would just want to note that you can do these without breaking it down further, but you can mess up. That's the thing.
Yeah, it's all your call on like how reliable you want to make your process. Do you want to go for speed and like skip a step, or it's pretty hard to mess up if you actually write out that Q0 to Q0 step though.
Like over here, for example, how do you go from Q0 to Q2 passing through Q0 or Q1? Well, you could mess up here because you can pass through Q0, so you can actually do... Oh, you can pass through Q0, but you can't pass through Q2. So technically, you couldn't do this, then back, because then you'd be using Q2 as a final state. So it's very easy to mess up if you do it with 2 states as intermediate states. Ideally, you'd want to cut down to 1 state. If you feel confident doing it with 2, then I would just do it with 2.
Yeah, I think as soon as you start to realize that there's like an infinite loop to handle, like in that case, you have to handle the loop between between Q0 and Q1. You have to handle that AA loop. As soon as you realize that loop is there, you're better off just writing out the formula for it, because you're about to do the same logic but in your head instead of on paper.
Yes, exactly.
Mm-hmm.
But anyway, let's move on for this one. Can you explain why it's CC here?
Beautifying the picture.
Up to you.
As opposed to what? Did you have a separate answer you thought about, or?
Oh, chat.
Because if you're not allowed to access Q1, then you're just going between Q0 and Q2 as many times as you want. So it's CC star. Because Q1 is not in your set of states. Otherwise, and in that case, there's not really, you don't have a lot of options.
Yeah, so CC here. So it's asking, how do you go from Q0 to Q0? You're allowed to go through... Oh, you know what? I'm just going to take it. Done. I'm just going to go back. Discard. I'll take a screenshot.
How big is this? Is this big enough? I guess I should zoom in again.
So here it's asking you, how do you go from Q0 to Q0, passing through states Q0 and Q2? Which means if you go to Q0 to Q2, back to Q0, back to Q2, back to Q0, back to Q2. So again, you want to start at Q0, finish at Q2, which we did here. And we pass only states Q2 and Q0 along the way, which is fine. And you can do that by doing CC as many times as you want. So it's CC star. Does that answer you? Okay, you get it? Okay. All right. I think we can move on to this one. So again, we've answered this term right here. Now we get to the second one. How do you go from Q0 to Q2, passing state Q1 along the way? So Q0 to Q2, passing through Q1, you can go A, B. So AB. Or you can just go to Q2 directly. So using C. So Q0 to Q2 is C, or you can pass by Q1 because we allow that. Okay, so that solves that one. Now this one is Q2 to Q2. passing through Q1. And remember, you don't have to pass through Q1. These are just the states that are allowed. You don't necessarily have to pass through them. So Q2 to Q2 going through Q1. So B, or epsilon, or you could just stay in place. Because again, we're going from Q2 to Q2. So you can just do nothing. And then finally, Q2 to Q0, going through Q1. Q2 to Q0, going through Q1. So Q2 to Q1 is a B. Q1 to Q0 is an A, so BA. Or you can just go from Q2 to Q0 directly with a C. And that answers the question. Now we have this term right here, which we can plug in. So remember, the term we're looking for to solve is this one, the one in green. And we broke it up into the 4 equal terms in yellow. And now that we have our answer, you can just plug it in. So you would essentially just repeat that 4 times. It would be, so let's say this is E plus, I'm going to call all of this X because I do want to show you guys something. So sorry. Okay. So now let's say our answer is E plus X because it's epsilon plus some reg XX, which is this. And we said that this is our answer right here, so I'm going to plug it in. So epsilon X this is for this, plus epsilon plus X for that one, then epsilon plus X starred for this one, and then epsilon plus X, which actually just simplifies to X star. It's not very obvious at first, but
oh yeah, true.
Yeah, it's not very obvious at first, but this is how I thought about it. I'm going to focus on the right term first here. This is essentially saying that...
Sorry, I just wanted to clarify. They won't give you any ridiculous example. Like, this is the most they can do while making it possible within the time limit. It will not be worse than this. There's no way.
Yeah, there's no way. This was also exactly on the assignment, which is why I knew how to do it. And again, they don't expect us to simplify, so you can actually just repeat this 4 times like that and plug it straight in. I'm only simplifying this because I just wanted to point something out that actually like makes you go, oh wait, now it opens your eyes essentially. But you don't have to know this on how to simplify, so just I'll explain it for those who are curious, but you don't need to know this. But over here, essentially what we're doing is we're saying that we can either have an epsilon or an X at the start concatenated with either epsilon or any number of X's we want, and we finish with an epsilon or an X. So we can have epsilon, 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 or epsilon, X, epsilon, so we just have one X, or epsilon, XX, which is 2X, or X, 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 which is 3 X's, or X, 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 which is 4 X's. This is just epsilon plus X starred, which is which is just x starred, because epsilon by definition includes, the star by definition includes epsilon. So that whole thing on the right simplifies to x starred, and by the same definition, if we have epsilon plus x starred, it's either no x's, one x, or many x's. That's just x star. So actually, if you look at this, this is the oh shit moment I was going for. When you remove Q0, right, and this is the term we calculated that gave us this big expression with x, it's essentially asking how you go from Q0 back to Q0, passing only all the other states along the way. So how do you go from start state to finish state? Once. Because if you were to move back away from Q0, then Q0 would be part of the intermediate states, which cannot happen. So essentially, how do you make one loop around the NFA? So this is this answer. Okay? And when we plug it in for the answer of the regular expression for the entire NFA, it's just we just showed that it simplifies to x star, because an NFA, you can take as many loops around it as you want, as long as you end up at the final state. So that's why the answer to this, which is what we started with, is just one loop, the regex for the first loop, so x with a star. Thought that was a little neat trick, and it just kind of like explains what this entire like recursive formula is actually doing. But yeah, kind of rambled for a bit. I'm gonna check the questions. I have a question as to why you break it down like this, such as it is not.
Thanks.
As it is not. One state Q and then work with it like that for the problems we are doing at least. Lucas, I'm not sure what your question is. You want to clarify? The one with the green? Yep. Yeah, you would just have to find the term in yellow.
Oh, are you guys confused by the fact that he has the line on top written out? Like the red line?
Oh yeah, that might be.
Because you don't need that top line. That was an example of like, oh, you could do this, but the second line is simpler. It's two different ways of breaking it up by choosing which state you remove. So it was showing off why removing Q0 is simpler. Yeah, I hope that might have been a bit confusing. Yeah, no, that top line is not necessary. You would just start with the second one. If you tried to expand out, or like if you tried to solve the first one, it would be more work.
Yeah. And the last yellow is just me showing my work. That's correct.
If they don't explicitly ask for it, then you're probably fine to skip a step as long as you're confident you can do that string properly.
Is it okay to have the longer method during the midterm? Yeah, that's totally fine.
Yeah, they won't be marking you on the correct one. It's just because it's a crunch against time. It's nice to know what the simplest way to do it is. Also, again, I highly recommend just writing like 0, 1, 2 rather than Q1, Q2 and everything just to save time. I find it so much faster. With how many of these you have to write. There's a very good chance they ask you to write out specific terms. They kind of guide you through it instead of making you just return the final string. Because I feel like they probably realized that was unnecessarily difficult. And because the 2022 is the older one where they did it this way, and then in the newer midterm they had us just write specific ones because they probably realized it worked out a lot better on just making sure you actually know the recursive formula and not really testing you on your ability to like know the whole process in the time crunch, you know?
Yeah.
So that's
It
my
is a
guess.
time
It's
crunch.
possible there
There's
could be
only
something like this, but I feel like there's a very good chance it's similar to ours, where you're just given like a specific like recursive, like just a specific formula you have to write out.
Can we leave it just in X? Yeah, I mean, the simplification, again, they don't expect you to do it. I just wanted to show you guys why it works out to be like that.
No, I think they mean like, is it fine to just write your answer in terms of X if you define what X is? And I think that'd be totally fine. Yeah, just to save you time to write, I think that's completely fine.
If you don't want to worry about any simplification or making any mistakes, then you take what we found over here and you just plug it in.
Peter, let me zoom out on the recording again so everyone can see questions in the chat. One sec. But on our midterm, I mean, you guys have our midterm, but we had some multiple. What's interesting was I feel like a lot of the time we had multiple choice that would be related to theory for like a more difficult assignment question. That's all I really remember us having from our assignments.
Yeah, I'm gonna pull up that midterm actually, and you touched on a lot of like the important concepts with the 2022, but there are some tricky questions that come up in the 2024 one that I actually wanted to talk about. And that, hold on, I'm just pulling it up.
Yeah, Jeff, I can't imagine any TA that would like see that you wrote that substitution and go, "Oh, it's totally correct, but I hate that they wrote this out instead of, or I hate that they wrote like X instead of writing out the whole thing, so I'm marking them wrong." Like there's no way anyone would do that. 2024
the 2024 is more lengthy, yes, and a lot harder. It is way harder.
Yeah, I mean, I 100'd it. Easy test.
Nice.
I actually don't know if that's true. I don't remember if that's true. I feel like I might have trolled like a single multiple choice or something.
The GOAT, Jacob.
He bleeds.
Okay. So, in the following questions, find examples of languages A and B that satisfy the requirements. So, give an example of a regular set A and a non-regular set B, such that A or B is regular. So if A is regular and B is not regular, can you find one such that their union is regular?
Wait, Gabe, can you give me like 2 seconds? I have an idea for something with the recording just to make this work a bit better.
Yeah.
I'm quickly, because I keep having to like, every time you go to, every time you start presenting, I want to like get rid of the chat, so I try to zoom it in. And then every time that we go back to answering questions, I try to bring the chat back. I should just have 2 separate scenes for this in OBS. That would be the smart way to do this. The smart way that I have not been doing this whole time.
Yes, Jeff, it is similar to what he discussed, but I don't think he touched on this example over here. Okay, but you should be able to get it right with what Jacob discussed, actually.
Yeah, I tried to go over any concepts you should need for this type of question in general. So I ideally have covered everything we need from this. This will be our test. We'll see.
I don't think you covered the union. I think that's why I said.
We kind of touched on it, but I didn't go too in depth into it. You're right. Yeah.
Yeah. So this one is very important to know. So if you have a regular set A that accepts some set of languages, a set of languages. Or, sorry, a language, which is a set of strings. So let's say this. And you union it with a non-regular set. Actually, I don't know why I'm drawing this. It's probably easier to just explain. So yeah, if you have an A being regular and you union it with a non-regular set, the only way you can do this is because the union essentially adds a component. Anything unioned that wasn't, so if you have A and you union it with B, anything in B that wasn't in A gets added to it, right? So what we're trying to do here is that we want a regular set A that gets unioned with B, B being non-regular, but A containing all the non-regular components of B so that nothing gets added to A. And what I mean by that is that if you have A being the regular expression, O starred, 1 starred, right? That's obviously a regular set because it's a regular expression. It's in the name. And you union it with B being the set of ON 1N, such that N is greater than or equal to 0. We've already proved in the assignment that this is not regular. However, everything in B, which is the non-regular components, are already in A. It's just not a requirement in A. So unioning them actually doesn't add anything. So A union B is just A, which is regular.
Yeah, so it's like about finding an expression, a regular one, that encompasses the entire non-regular set. Which is crazy. You know what's a really big set that encompasses everything and happens to be regular? It's the universal set. It's the universal set is totally regular. So yeah, that was when I did this, I just saw this, I was like, oh, holy, universal set, bam, done. So
that's actually the better. Yeah, this is just good to show, but the better example would be the symbol, the sigma star.
Any non-regular set is always still going to be encompassed by the regular by the universal set. Yeah, I just literally wrote like A equals U and like B equals like some. Like I think I just put some random set, like probably whatever. I probably put something similar to what Gabe put for B, and then I just said clearly their union is the universal set, which is regular. So
because everything in here already includes this.
Yeah, if you want a proper expression for the universal set, by the way, you can just do like A plus B star. Like if your language is just A and B, then A plus B star is the universal set.
I think what you mean is this, right?
Yeah. Yeah, so if AB is your, sorry, yeah, I was thinking of a different language, or a different vocabulary is the word here. But yeah, if your vocabulary is just A and B, then that's how you do the universal set. So yeah, totally valid. That's kind of what I did mention this at least, that for counterexamples and examples, you're almost always wanting to go to like the universal set and empty set. Those two break like almost all cases, like a lot of cases that would otherwise be true. Just very, like that's where my head goes immediately when I see these examples. I think both the example ones I wanted were doable with like empty set or universal set for all of them.
Yeah.
I don't think you need anything
Is
tricky.
A or B always regular? No, because if B has non-regular components that A doesn't have, then it gets added to the language, and since it's non-regular, you'd never be able to make a DFA for it.
Yeah, so if A is literally just like 0, 1, just the string 0, 1, then you like almost all of this union here is just A, B. It's just the set A, or it's just the set B. Like you still have to represent all those different strings of zeros and ones that you can't represent with an NFA or a DFA.
Because this would be...
It's an infinite set that's too complicated to represent with states. It'd be infinite states.
Yeah.
Something to think about, by the way, is it's impossible to have a finite non-regular set.
A finite non-regular set.
It's impossible.
Yes.
Because you can always hard-code it. You could always just hard-code it with an NFA.
Okay. Yeah. I think I know what you're saying.
Yeah, like you could always just... It would take a lot of states, but no matter how long it is, you could always... If it's finite, then you can always just make states, like a bunch of different paths and an NFA that represent it. The only case you run into things being non-regular is when they're infinite.
So over here, we'll just do A is equal to... I'll do yours.
Yeah,
sigma
I like this.
star.
This is just a very simple example.
B is equal to
something
that's non-regular.
Mm-hmm.
So this is you should remember at least a couple of examples.
This is my go-to. The A and BN is my go-to for sure.
So A or B is just A, because A is already everything. You cannot add anything more. B has to be a subset of A, correct?
Yeah.
That is correct. Okay. Give an example of a regular set A and a non-regular set B. Okay, Jacob, you already did that one. That one is pretty easy. This is just...
Oh, yeah, this one's easy. Yeah. This is the opposite, right? I said the universal set is used like for union because it encompasses B. In this case,
Yeah.
we're doing intersection. The empty set will kill whatever B is. Doesn't matter.
And remember, this is regular.
Yeah. So empty set and universal set are regular, and they break so many cases.
So A and B is null, which is regular. Give an example of a regular set A and a non-regular set B such that AB is regular. Oh, what do you know? It's the
Oh my
exact
god,
same.
we do it again. We do the same thing again. Oh yeah.
We do the same thing.
This is a real tough. I literally looked at this page and I laughed. Like when I saw like this is the front page. I'm like, oh, I don't know what we're gonna get. Whoa.
So AB is null, which is regular. Okay? That is good. And then this one actually is pretty tricky.
What's the next part?
The question 2 from 2024.
I don't actually. I asked if you had 2024. I don't have our midterm somehow, so.
Oh.
I haven't seen this since last year. I'm seeing this all for the first time in a while.
Okay. So there is actually a trick. I'm going to start with the last one first.
Oh god, this. Oh yeah.
Yeah. So if you have some set A that's regular, which of these are either regular or not necessarily regular? So if A is regular, A and this, is that regular? So this is actually meant to trick the first people, like the people who just see A, N, B, N, and automatically say that this is non-regular, which means that
Oh, that's so funny. Oh, that's evil, actually.
Yeah.
That's great.
So the answer is that what you would think, like if you weren't paying attention to this part, is that this is non-regular, so that their intersection is not necessarily regular. But actually, the key to non-regular sets, such as A, N, B, N, N greater than 0, is that you would require an infinite amount of memory, like Jacob said.
Yeah, I'm glad I touched on this earlier then. Yeah, it's because it's finite, it would always be possible to hard code no matter how complex it is. It's when you get to like weirdly complex infinite sets that require memory that you can't do it.
Yeah, because over here, you can literally hard code this. You can make, like Jacob did, where you do A, and then 1B to come back. And then if you do another A, you would just do 2 of them.
Yeah, just do 10 of these, and you're done.
And then
You've done it.
Yeah, and you do 10 of these, you're done. So regular, A is regular, this is regular, call this C is regular. So A and C would be regular. So the answer to this is actually
Yes,
regular.
Peter, that's correct. If the condition was that n is just more than 1 and it was uncapped, then it would be unsure.
Yeah, it would be not necessarily regular. Okay. Now, I guess I'll just work back. I'll work up.
I guess we should talk a little bit about the set theory with A real quick.
Yeah,
because
sure.
if A is some like normal regular expression, you would expect A to actually like kill the non-regular parts of A and B in, you know? Like if A was just the regular expression AB, then even if we had a non-regular expression on the right, then you would expect the intersection to still just be AB, so it's still regular, right? But we care particularly about the case where A is the universal set, or A is the set of all, like A of some for some number and then B for some number. Like either of those would result in it just being the right side there, which is bad, because if that was non-regular. I don't know if that made sense. I hope it did.
Not sure what you meant.
I think it's important for this type of question to identify that like A is allowed to be anything. So if A was a simple regular expression, if A was just AB, just the string AB, then even if the right part was like didn't have to cross out the less than 10 restriction. Just
Oh,
no, just
yeah.
the less than 10. Yeah, just the less than 10. Like literally just like leave it as one less than n. Like yeah. So now that part's non-regular, right? So if this is the case, this intersection though is still regular, you know?
Yes.
So it's important to envision like A as being the universal set, or A as being some number of A, some number of B, you know? I just feel like
Wait.
I felt like we didn't touch on that, so I wanted to at least mention that part. That this is only non-regular. Or this would only, like, even if that part on the right was non-regular, this would only be non-regular under the condition where A is the universal set or something larger than the right side. Something that encompasses the right
Oh,
side.
yeah, I see what you're saying. Yeah,
Yeah.
yeah.
So it's hard to explain
it
without
would
being able
only
to write or anything, but like
it,
that's important.
A is a superset of what's on the right.
Mm-hmm. If that's the
Because
case,
then it just gets reduced to B.
yeah.
Okay. But if A is a subset, if A is regular and is a subset of whatever was on the right,
Then
then
it's
it
still
would
regular.
still be regular. Even okay, that's like actually a good point.
Mm-hmm.
So, just in case this wasn't clear, I'm gonna rewrite it. So if we had A and ANBN, n greater than 0, and A was was a subset. I'm gonna call this B over here. If A was a subset of B, so let's say A was just the set AB, intersecting AB with AN, BN, n greater than 0 would actually just give you AB, which is regular.
So there's kind of two parts to this type of question. It's you have to consider, hey, is the right side, like, is the other part even non-regular, or is it regular? And you also have to consider all your possible options for what A can be. So, yeah, this one was tough. I remember this page being fun.
Yeah. But in our case over here, we know A is regular. We know this is regular. Without even thinking, we can just say A and B is regular.
Yeah.
But in the case where the right side wasn't regular, it could still be regular. That was the point, which is a very I like.
Yeah.
Yeah.
Which again is fine
Good
for
eye,
our
Jacob.
question though, because we're asking like, is it always regular or could it not? Is there the possibility that depending on A, could it not be regular? So at that point, the answer does become it's the answer becomes not necessarily regular. Because you have to choose A as a superset. Yeah. Okay.
Okay.
Which one do you want to do next?
You want to do this one?
Okay, what was the idea here? So reverse is just, so X is some string in A. So we're saying it's just the set, it's just A but reversed. It's literally just every string in A but reversed.
Yep. So if A was the sets like AB, AAB, etc., is this language here where everything is reversed? So instead of AB, it's BA. Instead of AAB, it's BAA. Is that still regular? So rev of A. Is rev of A still regular? Yes, it is, Peter.
Yeah, absolutely. You can take a regular expression that represents this and flip it around. Good job.
Or in terms of, if you want to think of it in terms of phase, you flip all your arrows and you make your final states. You make your final states non-final. You make your final states start states, and your start state a final state.
Yeah, so just swap your accepted and start states and all that, and yeah.
So yes, that one is true. So A or this part.
Ugh.
So the part on the right, without proving, you can. I think it's. Yeah, is it infinite? Sorry, is it a non-regular? I think it's a non-regular. Yeah,
This should be
it's
non-regular.
a non-regular.
A to
Should
n
be non-regular.
factorial is definitely non-regular. I think you probably don't even have to think about that at this point with your intuition of the course. Like, yeah. And so then what's our worst case for A? Our worst case for A is that A is just the empty set, because then our set is entirely dictated by this non-regular thing on the right. So there's a possible world, depending on what A is, where this is non-regular. So again, doesn't matter that it's not always non-regular, but because it could be non-regular, depending on A, we have to put non-regular.
Union those two. Then everything here gets added to this. The answer is just that, which is non-regular. So we've come up with a counterexample where it's not necessarily regular. It could be, but not necessarily. Okay. So, not necessarily.
Yeah, I'll be right back. I just gotta refill my water.
Okay. These are a bit harder, actually, because it's hard to even imagine what they're asking. If you see any set with n with an upper bound, is it always irregular? No, because you can easily come up with a counterexample. The set a to the power of n with n greater than 0 is regular, because you can just make a start and final state that loops on a. And that is regular.
Okay, I'm back.
Okay. Jacob, you wanna explain these?
Yeah, I gotta remember them first. Okay,
Yeah.
what's going on here? Okay, their definitions seem similar. So, X is a contiguous substring of Y for some Y that was in the regular set. So this is just the set of all possible substrings of A, of any string in A. So I think all you do for this one, if you want to visualize an NFA, is you could just set every state to be accepted. No, I don't know if this works. Because in theory, you can set every state to be accepted so that you can, like, stop early. But that's only all prefixes. Is that making sense so far? Gabe, I don't know how you I don't know what plan you had for how you wanted to tackle this one. The way I thought about this on the test though was I was thinking about how this would work for like an NFA, and just changing the accepted states. So my initial thought was that okay, if it said all prefixes, you can easily do this because you just set every accepted state. You set every state to be an accepted state. This lets you just stop early, and you can think of it as that you're stopping early at any point.
Yes. Okay.
But then there's like, okay, how do you start early? But I think you can kind of like just basically duplicate the NFA and make every state, or yeah, you could just make you don't even need to copy it, just make every state a start state as well. So you can start anywhere and end anywhere, which should give you this set. So you have an NFA for it.
That's actually a better explanation than I had. Yep.
Contiguous just means that the thing is, I mean, I don't even know why that word exists because I feel like I always just think of it as synonymous with the word continuous and like it works.
Yeah, continuous.
Yeah. I don't know what it's trying to say. Honestly, I think if they got rid of the word, everyone would interpret it the same way. Like it's telling you like you can't, like let's say my string is, can you write a quick example for me? Write out AABAA. Yeah. It's just saying that like AAAA doesn't count. Like you can't have like a sudden gap in your substring, you know? Like it has to be a continuous segment of the string.
Honestly,
I
don't
think that's
even
all it
just
means.
remove that word. X is
Yeah,
a
literally
substring.
ignore that word. That word is so not important because obviously that's what substring means. Like,
It's literally redundant to say contiguous substring, I guess. But yeah, that's a good explanation. You could, so essentially it's saying that are all the substrings, so let's say A is some set like A, B, A, B, B, etc. Are all the substrings of all the strings in A, can they essentially, is that a regular set? Can they be represented by some NFA? Well, Jacob's solution was that if you had some NFA, if you had some NFA like this, that takes in a string and moves all the way to a final state, a substring would be like, for example, if this accepts the string AB, B is obviously a substring. So how could you modify this NFA to accept B? Well, you could just put this as the start state right here. So you would start here and you would just accept B. Okay? Now, if you make this a little bit more complicated, where we put B, C, and we have this obviously accepts ABC. So the substring of ABC could be AB, BC, B, C, A. So if you make everything a start state and a final state, then you could essentially just start anywhere and absorb all these substrings, and you would always accept that substring. So
yeah, it just lets you start anywhere in the machine, end anywhere in the machine. There you go. You can accept any substring.
Which is essentially what a substring is. A substring is anywhere in that string, you can start and end somewhere, and that counts as a substring. So you start here and you end here, you start here, you end here, you start here, and that's essentially what Jacob did. That's a very good explanation.
So it's just there's so many different ways to think about regular expressions, and for each of these, you kind of want to try to identify, okay, what's the easiest to rationalize for like the description of this set. Like to me, if I'm trying to picture, okay, a substring is about starting and stopping in different spots, then visualizing it as a machine with start and end states is definitely a lot easier than visualizing it as a regular expression. But for the other one, that was about like, oh, reversing the order, to me it makes more sense to flip the regular expression that you would write than it does to necessarily just flip the direction of the arrows. Like my brain doesn't immediately go, oh, flipping the direction of the arrows for sure works. There's nothing wrong with that. Like I'd have to think about how loops work and all that. I'd be a little worried that maybe something breaks there, you know? So I think you kind of have like different options or different ways of visualizing regular sets. You want to find the best one for the question you're dealing with, for this type of set that it's describing. It's best not to just stick to one, like, oh, you always think of regular expressions for any of these.
Yeah, I mean, see, man, I think in everyone's definition of substring, AC is not a substring.
Mm-hmm.
So the contiguous just confuses more people than it clarifies to people.
Yeah, I've never seen substring ever mean that you can just have a gap in the middle.
Okay, and
okay,
this one,
actually, okay, Peter wrote out a. Let me hop back to my other. Now I can try my other scene. I have my other scene that shows the chat. Oh, this, I feel like a professional streamer now. Okay. Peter has a question about a specific graph that he wrote. I think, Peter, are you asking how does the whole idea of like making every accepted state, or making every state accepted and making every state a start state? You're asking like how that works for this graph? I just want to clarify I'm understanding the question here correctly. Yeah, okay. Gabe, do you have a way of, can you open his picture from the text?
Yes.
Yeah. And then I'll hop back to my other stream layout. Oh my god, I feel so cool. Dude, it does this epic fade effect when I click the other one. Oh, I love this.
Okay.
Okay. So, what's your start state here? Am I assuming Q0 is the start and Q4 is the final? Okay. Or what am I assuming is the start and final? because you're talking about making Q4 a final state. So I think you had something. Do you have Q3 in mind? Oh, okay. Sorry, you're right. So technically you'd have to add an addendum to this. It's any state that can reach the final state becomes a final state. You're right. It's not just every state. So Peter here is saying that if Q3 is your final, then if you can take Q4, then if you make Q4 an accepted state, well, now you've added the string 2 to the accepted strings when that wasn't a substring initially. So it's only any state that can reach the final state, or that can reach a accepted state, that becomes an accepted state as well. Which that part kind of makes intuitive sense. Like, again, you're trying to just allow you to start anywhere earlier in the string. You're not trying to let yourself end early in the string. You're not trying to let yourself end in normally inaccessible spots. So the logic still followed. It's not like you have to worry about considering edge cases like this. We came up with the logic for a reason, and it still followed. So that's fine.
Yeah, I mean, you can come up with a lot of edge cases, but as long as there's a way to tweak the NFA to deal with those edge cases, then it would still count, which is okay.
I more just wanted to follow like the logic that we had made sense, and it's not really like from like. I don't want you to see this and worry about like missing edge cases when you come up with your nice example of why it's probably a regular expression.
That's a very good counterexample, though. Yeah,
that is a good counterexample.
Actually, it's really like you want to make sure that, that any, like a substring is essentially a state where that leads you to a final state.
Mm-hmm.
This cannot lead you to a final state, so it's not even cannot be a substring.
Yeah. But essentially, I think what's important to note is this is not a like minimal FSA for the same language. For any practical, FSA, what am I saying? For any practical DFA that represents the language with the fewest states possible, like you could just make every state accepted. There shouldn't really be, only for an NFA. For a DFA, you need like a garbage state. Definitely don't want to make that accepted, right? But if you're trying to make like the smallest NFA possible to represent a language, you wouldn't have that state. You wouldn't have that state. You know, it wouldn't be there. I don't know where I was going with that. I just thought it was important to note that that's kind of like a specific example. You wouldn't see that state is not needed at all for a language. There'd be no language that would require some weird state like that.
Okay.
Okay. Anyways, what is even the difference in B?
Yeah, the next one's pretty easy. It's just saying, if you take all the strings that have Y as a substring, Y being the strings in A. So all the strings. Yeah, superstrings, exactly. So is the string YZ, where Y is in A, regular?
Oh, yeah, this is also easy. Okay, I have my answer.
It's pretty easy. Yeah. I mean, you just use the NFA for this, and at every final state, you self-loop on every symbol. We did this in the assignment.
Oh, I would have done this with a regular expression. To me, I would literally write A plus B star, then my regular expression. They just do some squiggles in the middle for my regular expression.
Oh, and then just
A plus B star on the end. Like you would just have your regular expression in the middle, surrounded by A plus B star.
Oh yeah. Actually, you know what I saw? It's A.
Yeah, or you can do that. Yeah. Honestly, for this, I recommend writing like AB star, because we know that AB is our language. Like, see that they've kind of clarified that AB star is our language in this case. I would usually write the regular set as that. A plus B, yeah. Or you can do like the set AB the same way they do it for the A description. You could do quiggly brackets, A comma B star. I don't know, either works.
So yeah, this question is asking, is the language that has all the strings in A as a substring, is that regular? Well, how do you obtain that language? You can concatenate it with the universal set. And again, we concatenate it because we know this is regular. A is regular, and that is regular. Now this language has all the strings in this language contains A as a substring, and that is also regular. So yes. Okay, and I think that pretty much wraps this up.
Yeah, because I think 3 was similar to the other 3, which was easy, right?
Yeah. There's only like the I'm gonna go over question 1 very quickly. We've already been doing this for 2 hours, but I'll go like super quick. Just pasting the. So these are just true or false.
Oh, we had this. Okay.
So, is there a language that where the DFA has 100 states and the NFA has less than 20? Yes, because if an NFA has any states, then the most states the DFA could have is 2 to the power of n. So if the NFA has 20 states, the most states the DFA could have is 2 to the power of 20, and that's a lot more than 100. So yes, there exists an NFA that has less than 20 states, but more than 100 states for the DFA.
I think I got this one wrong. I got one of these wrong. That was I remember now. I think this one I didn't know because I didn't know that property.
I see. Okay. Assume M is a DFA for the set, and N is an NFA. Okay. So M is a DFA, N is an NFA. Then we can always find a regular expression such that AB. So a regular expression means that it's regular. We know a DFA is regular, an NFA is regular, and that the concatenation is closed under the concatenation property. So if A is regular, B is regular, then AB is regular. So that is correct. It is true.
Yep. Peter's asking, do we know the min? Well, for the number of states, the best case is if your NFA just represents the DFA, or hang on, what am I trying to say here? Is this what I'm trying to say? Like, there's a case where they're the same. There's a case where they're the same, basically. Like, the best case is that the number of states for the DFA and the NFA are just the same, because the NFA is just the DFA. Like, they could just be.
Oh yeah. But you can't.
Oh no, sorry. Oh, I'm looking at this wrong. Sorry, no, we're talking about how low it can go. Sorry, I'm brain farting here. Sorry, the DFA guaranteed has more than 100. We're talking about the most you could reduce it by. No, I don't actually know that. No. I don't know what I'm trying to say there. I read that question completely wrong. Yeah, I don't know if we know the minimum.
The first one is not false. The first one is true. Because if an NFA has less than 20 states, say 19, then a DFA could have more than could have up to 2 to the power of 19 states. So yes, it's true because of the existence of the best case.
It's just saying there exists a language where both of these are true, which is true. There does exist a language, is all it's really saying.
Yeah.
The wording is completely correct.
Okay. This one is saying that if A is a language, assume N. Okay, so N is some NFA with that formal definition. And N2 is the same as N, but with all the states flipped. So all the final states became accepted. Sorry, all the non-accept states became accepted, and all the accepted states became non-accepted. Can we conclude that the N2 is the complement of N? And the answer to that is no, because to get the complement, so if you have a machine, that's only true for DFAs where to get the complement of the language represented by DFA, you can flip the states. But in this case, it's an NFA, so it's not necessarily true, so it'd be false. False. True. True. This is saying, this is kind of what we just touched on right now. Assuming there is a DFA M defined by this, we can always find another DFA M2 with exactly the number of states, such that that second DFA is the complement of the first one. So LM2 is the same as the complement of M1 that has the same number of states. Well, yeah, you just, if you flip the states, the accept states, the non-accept, and the non-accept accept states, you're not changing the number of states. So yes, true.
So this only works because that is true, that flipping the accepted states gives you a DFA for the complement. That is not true for NFAs. If this question said NFAs instead, this would be false.
Yeah. So the key here is just DFA, and the reason this is false is because it's an NFA. And if someone doesn't, this notation isn't like widely used, but QF is like saying the set, like Q is some set minus everything that's in, that would be an F.
Yeah, so this is called set difference.
Set difference. So now the final states become everything that wasn't final and vice versa. Let A be a regular language, let M okay. So you have a machine M1 with 10 states, DFA, and you have some regular language A over the, so defined over the, we don't know what that language is. It's just a language that accepts some combination of the strings A, B. So we try all strings of length at most 100, and we observe that any string that's in A, so we observe that if X was in A, then X was also in M1. And if X was in A, was not in A, then it was not in M1. Can we conclude that the language of M1 is equal to A? And the answer is no, we cannot, because, and I'm going to answer that by doing this one first, and you'll see why. So this is so this question is asking the same thing as the one above, but now there's two DFAs, M1 and M2, each with 10 states. And actually there's a law here that says that if you have two DFAs, then for them to not be equal, so let's say there's a DFA D1 with N states, a DFA D2 with M states. If D1 is not equal to D2, then there exists a string S such that the length of S is less than N times M. Which, all this to say that to check if these two DFAs are equal, there should be a string that's length 10 times 10, 100. There has to exist a string that's length 100 that is accepted by one by not the other. But over here, we tried all the strings of length 100, and we observed that if it's accepted in the first one, it's accepted in the second one, and if it's not accepted in the second one, It's also not accepted in the first one. So can we conclude that they're the same? Yes, we can, because if they weren't the same, of all the strings we tried that were length of at most 100, we would have found at least one that we call the distinguishing string. Which is why over here, we don't know the length of the regular language A. A could be a DFA with length, with let's say 100 states. So the distinguishing string would have to be length 10 times 100, which is 1,000. But we only tried the strings of length at most 100. Which means we cannot conclude. We would have had to try all the strings up to length 1,000 to conclude that. I hope that was clear.
I hate both of these questions. I guessed them right on the midterm.
Oh, you guessed them?
Yeah. Like I said, I said before for the top one, like I didn't really know a lot of the properties between like, oh, you multiply this by this.
Yeah. Honestly, I didn't know this property until I was looking over the...
I think, sorry, the second last one here, like the first one we were looking at out of these two, I did know, because this was like a pretty simple example where you choose a regular expression that intentionally, like let's say the DFA is just like A star, you know, it's just a simple one that represents A star.
Yeah.
Then your regular language could be the set of all A's, like all strings of A, like up to length 100. And then, you know, it stops there. Like it could be A up to A to the power of 100.
Yeah.
And then it just stops, and then that was a pretty clear counterexample, you know?
Oh, okay.
So I had this one was an easy one with a counterexample. It's the ones that don't have a counterexample that I always stare at for a while, wondering if they're true or not, or if I'm missing something, you know?
Yes. Okay, so what Jacob was saying, I'm just gonna write it down, is that Peter, I'll answer your question in a second. But what Peter was saying was that, Jacob was saying was that if A over here is just A star.
No, I'm letting, so M1?
Other way around.
Yeah.
If M1 was a...
And technically you should be writing L of M1 for being really specific here, yeah.
Okay. And A is A, all the way up to like A to the power of 100. If we observe, well, clearly they're not equal because A only A only accepts 100 repetitions of A, whereas M1 accepts all repetitions of A. Well, over here, we tried all strings of length at most 100. So we tried all of these, which are accepted here and here. But we cannot conclude that LM1 is equal to A because in this case, we just found a counterexample where they're accepted by both and what's not in them is rejected by both, but they're not equal. And I think that pretty much concludes.
Yeah.
Yeah. The first two are easy.
Go ahead. Sorry. Go ahead first.
No, I was gonna say the first two that are not in this, that I didn't like screenshot. It's just they should be straightforward.
Okay.
But yeah.
Sorry. All I was gonna say was then my logic for the last one when I got to this, because again I didn't really know how to what the logic was to prove it. But I was kind of thinking something along the lines of like, okay, clearly my counterexample for the previous case required basically the machine to be infinite, while the regular expression was kind of finite. But it was like the regular expression was like a hard-coded language all the way up to 100, and then it was able to stop. But I was like, with less states, probably can't do that. So it seems true to me.
Okay.
That was like all I had. That was the entire intuition behind guessing true on this last one here. I was like, yeah, 100 seems like enough.
Yeah.
I don't know.
That one's like, if you don't know this rule. Oh, Peter, I don't understand the relationship between the number of states and the length of the string. Okay, if you have a DFA M1, a DFA M2 with N states and M states, then if M1 is not equal to M2, then there exists a string W such that the length of W, so the length of the string, is less than N times M. Where W is accepted in one and rejected in the other.
Is this like by product construction or what?
I'm not sure. I just pulled it up.
Okay. Because I wonder if the theory is like if you were to do the product construction of this, that you would see that it doesn't actually match the like either the like it doesn't match one of the languages, you know?
That would make sense, actually.
Yeah, I wonder if that's where this comes from. I don't know.
The proof is left as a reader to the as an exercise
left
to the
as an
reader.
exercise to the reader. Ah, yes.
Can you explain why the second last one is wrong?
So we kind of have a counterexample up at the top there.
Yes, the previous one is false because we don't know the length of A. Yes.
Yeah, because A is unbounded, it can be so like because the number of states is unbounded, you can make a really complicated thing where it's hard coded for all those strings up to length 100, and then its behavior suddenly changes, it deviates from what the machine does for those strings of larger length. So the simplest example is just a set that mimics the language all the way up until 100 and then stops. Because any finite set is regular. So if you just have a finite set that mimics it for that whatever that length is and just cut it off there, you have a counterexample. You have a regular language that does not match the behavior of the DFA.
So we just mimicked, we came up with an A that mimics the DFA with 10 states for strings of length 100. So we hard coded it because, again, the length is unbounded. We can hard code as many things as we want. And then anything that's like 101 length would not have been caught by our checks.
Mm-hmm. Okay, I think we're good on that one.
Yeah.
Cool.
I think that wraps up pretty much everything.
All right, then.
Yeah, the last question is the same as what we did for the recursive formula. I think over that.
But yeah, if you're really curious about like why that property exists, maybe yeah, I'm recording it, Philip. If you're curious about why that property exists for the last question, maybe go look into how product construction works. Because I think if you were to, you'd expect if two languages are equal, you would expect their intersection to also be the same, right? You'd expect it to match both of them. So if you do the product construction, I wonder if there's something there. It's not really coming to me right away, but I feel like there should be something there, some kind of property you could check that were like, if an accepted state is not what you expect it to be, I don't know. I don't know if this is making sense. It's gotta be something with the product construction. I don't know, but I can't explain it right now.
I feel like it's definitely has to do with product construction.
But I don't know. That idea is not going anywhere at the moment, so it is what it is.
Because you take all the pairs, Q1, Q2. Yeah, I don't know. That's an exercise for you, Jacob. Okay. All right. That pretty much wraps us up. If anyone has any questions, just send it over in the chat as usual. Someone will answer.
All right, I'm banning Pavlos. Wait, let me switch to my other Epic display. Oh yeah. Wait, Gabe, have you done other study sessions before?
That is my first one.
Oh, okay. I was curious what Jeff was saying.
I think it's because yeah. Whoa. Oh yeah. 2C.
Oh,
GC.
okay,
Hello.
okay. Let's go. Oh, hello, Senna.
Hello, Sana.
Hi guys. Thank you guys for hosting this. Sorry I had to drop out so last minute.
I mean, this
You,
wasn't
like,
really
you
even like a CSS thing, anyways. I just volunteered to join up
Yeah.
because I thought it'd be fun.
You hopped on as soon as we were done.
No, I've been on for like the last 30
She's
minutes.
been
I
in
texted
here, yeah.
Jacob. I was yeah.
Oh,
Look at you.
okay.
You read my text and you didn't respond.
I was
Guys,
busy
Jacob is
doing
an
the
ass.
session. Well, could you imagine that?
Okay, guys. Have a
Good
good
job.
night.
Yeah.
Thank you.
Good night, everyone.
I'll do more. For sure.
All right. Good luck
I
on
was
Tuesday,
gonna ask-
everyone.
How are people feeling right now? Scale 1 to 10 for this test.
I think some of the
Wait.
multiple choice questions are a little scary. I think the rest is probably fine. Jacob is my comfort streamer. Let's go.
Yeah, I feel like some questions are going to be tricky, but the recursive one is pretty free. All the tricks you showed with the null set, concatenating and destroying anything else, that's pretty neat.
Yeah.
Without
I'm gonna
those,
end the
though,
recording.
like,
I'm gonna end the recording here. So goodbye, everyone on YouTube.
Oh, it's
All right. Thank you for joining. Farewell.
okay, I'm gonna head out. I need some more.